Okay, so continuing our applications of polynomials, we're up to example 4 here. And we have a rectangular sheet of cardboard measuring 1 metre by 1 metre, has 4 equal squares of edge length x centimetres cut out from the corners. The sides are then turned up to make an open box. Okay, the first thing I want to be really careful about here is that my side lengths of my squares are in centimetres and my side length of my cardboard is in metres. So we need to be consistent about that, or we're not going to have an equation doing what we need it to do. So let's work in centimetres instead. So this is 100 centimetres by 100 centimetres. Okay, so what we want to think about here is what's actually happening. So if you imagine folding along these dotted lines, folding the side flaps up, we're going to create a sort of flat tray. Well, if x is small, it'll be a flat tray. If x is bigger, it will be more like a box, okay? That looks something like that. The height of that box will be the length of the flap, right? Or the width of the flap. So that's going to be x. And then if we think about the side lengths of the base of the box, it's a square, okay? So looking at this length here, we're going to have 100 centimetres take away the 2x, which is the rectangles that were cut out, okay? So this is going to be, this is going to be 100 minus 2x. This is also going to be 100 minus 2x. So we're finding volume. Show that the volume is, okay? So again, it's not about using that formula. This question in my head, I'm reading it as find the volume of the box, find an equation for the volume of the box. Hint, your answer should be this. Okay, so volume we know is length times width times height. So in this instance, we're just multiplying those 3 dimensions together. So we're going to have x times 100 minus 2x times 100 minus 2x. Okay, so we have x times 100 minus 2x all squared. Now again, it's not about skipping steps here. We need to be really clear about how we're getting to this end result. Okay, so our equation doesn't quite match the equation given in the question, but it is the same equation. We just need to be able to manipulate our equation to make it match what we're being asked to show. So if we look at the bracket, there's a common factor in here of negative 2. Actually, I'm going to leave it as positive 2, or else I will be getting a different answer. So 2 times 50 minus x. So factoring out that 2 is allowing me to see that 50 minus x that I'm trying to get to. Sorry, and it's all of that squared, which is important. So now if we're squaring what's in the bracket, we can square the 2 and square that bracket. And so we get x times 4 50 minus x squared, which is what we're trying to show. 50 times 50 minus x all squared. Okay, so we've got our equation for the volume. We've shown that the volume is this. Again, if you weren't able to do that, you can move on to part B without doing part A. You've got the equation of the volume. Part B is sketch the graph of V against X for suitable values of X. So again, thinking about what's relevant in this question, sketching a cubic graph. So again, coming back to what the maths of it is. This could be exercise 5B, sketch the graph of y equals 4x times 50 minus x all squared. Okay. So again, not necessarily launching into our CAS straight away. Let's think about what it looks like. It's quite similar to the last one we drew. So obviously we know that we've got V is 4x times 50 minus x all squared. So we're going to have x-intercepts when x equals 0 and when x equals 50. And this time the 50 will be, sorry, not the cut, the 50 will be where we have the touch, the turning point, and at x equals 0 we'll have a cut. Y-intercept will also be 0, or V-intercept in this instance. Alright, so again, we should be able to draw our graph. So we can think a bit about, we might draw it in pencil and then think about what we have. Again, we've got a negative cubic. It's going to cut at 0 and touch at 50. Have I got my graph the wrong way around? No? Okay. So cutting at 0 and touching at x equals 50. Sorry, I'm just going to move my y-axis up a bit. Actually, we don't have a negative cubic here because the negative x is being squared. So if we were to expand all this out, we would still have positive x cubed. Good, I was a bit worried about that, it didn't make sense. Let me move my x-axis down here again. Okay, so x, y, or v, sorry. So our graph is a positive cubic. It is going to cut at 0 and touch at 50. Okay. Now, in this instance, we need to be a bit careful here in thinking about the suitable values of x. Obviously, can't have negative length, can't have negative volume. It would appear that the rest of the graph is relevant. But what we need to think a bit about is if x was to be, so this point here is 50, 0. If x was to be something bigger than 50, what would actually happen here? Let's go back to the box. So if x was 60, for example, let's have a look at the dimensions of the box. So the height of the box would be okay, it would be 60, but actually what we would see is happening is that the two orange lengths on the sides of the box would be 100 minus 2 times 60. So they're actually going to be negative lengths. So that doesn't make any sense at all, okay? So actually what we also need to think about, we know that x has to be bigger than 0. My apologies. We know that x has to be bigger than 0. But we also know that the other side lengths, 100 minus 2x, has to be bigger than 0, which means that 100 has to be bigger than 2x, or 50 has to be bigger than x, i.e. x has to be less than 50. So we're actually also not interested in this part of the cubic out here, okay? So we are only interested in this part. So in terms of the suitable values of x, the things that are actually possible, given that what we're doing here is creating a box, is this. Okay. So I'm going to rub out my pencil underneath. I don't need those bits. And there is my graph of v versus x. Now we also want to label all intercepts and turning points. So again, all intercepts, there's only 2 of them. I'm going to label 0, 0, even though, you know, it's a bit, we don't really need to, but no point in not. Give the x and the turning points with their coordinates. Give the x coordinate of the maximum turning point correct to 1 decimal place and the y coordinate correct to the nearest whole number. Okay, so we are going to need our CAS and the graphing screen of our CAS to do this until we have some algebraic tools in semester 2. So over to the graph on my CAS, tab to open up my entry line. I'm going to put my equation in. It is 4x times 50 minus x all squared. We draw the parabola. Looks like a straight line, but that's because our scale is nowhere near where we need it to be. We know the other x-intercept is at 50, so I'm going to edit the positive maximum x value to be 60, so past that intercept at 50. All right, and again, obviously, this is a very, very tall graph. So I'm going to again go into menu 4.1 because if I'm going to make the y maximum really large, like I think thousands in this instance, then I'm also going to make the y minimum a bit bigger than -6. Otherwise, you'll find that your x-axis ends up right at the bottom and then becomes sort of hard to see what's happening. So actually, let me just show you what happens when I do that. So if I just adjusted this number up here to be 1,000, now my x-axis is so close to the bottom, it's sort of a bit hard to see what's happening. So I like to also make the negative y value a bit bigger as well, so we can still sort of see where the x-axis is. We clearly also need the maximum y to be much, much bigger than 1,000. So I'm going to go into menu 4.1. I'm going to make y minimum -500, and I'm going to make y maximum 8,000. Might even need to be bigger. Way bigger. Okay. Menu 4.1. Let's make y minimum -1,000 and let's make y maximum 20,000. Okay, still menu 4.1. Maybe, I only made it -100, sorry. So let's make that -5,000. Let's make that 100,000. Okay, now we can see what we're doing. All right, so we want to know where that turning point is. So menu 4.1. menu 6, maximum 3. Again, selecting somewhere to the left and somewhere to the right. Now, I already drew my graph in because I wanted to talk about how you should really think about what it looks like beforehand, but you probably should calculate where your turning point is beforehand, just so you can get it in a relatively correct position compared to the 50 that you've got marked on that x-axis. Mine is a little bit too central, so compared to what I'm seeing on the calculator screen. Okay, so give the x-coordinate of the maximum turning point correct to one decimal place. Great, we're seeing that on my CAS, 16.7. And we want to give the y-coordinate to the nearest whole number. Now my CAS has reverted to scientific notation because this number is very big. So it is 7.41 times 10 to the power of 4. I don't write that down. I'm going to adjust how many digits I see so that I can see it to the nearest whole number. So again, clicking once to select, control menu to right click, attributes, increase the precision value higher than 3, and all of a sudden you can see the, well, not full extent, it's still a rounded decimal, but we can see enough of this number. So we want nearest whole number, we're going to have 74074, okay, and so we've got our graph completed. Find the value of x for which the volume of the box is 768. Oh, now that's tiny, sorry. I meant to edit this question last year. Let's change the question. We can see that compared to the maximum volume of 74,000, that 700 is ridiculously tiny. Okay, I'm going to make this different. Let's say find the value of x for which the volume of the box is 30,000 cubic centimeters. Okay, so I'm just changing the question. It's not a good question. All right, so in this instance, what we're really looking for is essentially, so if 74,000 is up there, 30,000 is going to be somewhere here. So we want to find the value of x for which the volume of the box is this. Okay, now there's actually going to be two values, and again, this question, I suspect I changed the earlier parts and not this part. Really, this should say value or use to indicate there might be two answers here. So in this instance, we're definitely going to get two values of x. We can see that from what's happening with the graph. So find the values of x for which the volume of the box is 30,000. So again, an equation is needed to be solved here. So we are solving v of x equal to 30,000. We're going to solve that for x. We don't need to write that. That's very clear when x is the only variable. Now again, I can make use of my definition. My v of x is actually f1 of x in the calculator. So over here, menu 3.1, f1 of x equals 0, sorry, not 0, equals 30,000 for x. Okay, we get 3 solutions with the CAS, but remember that's because we didn't draw the whole graph. We stopped the graph at 50. There's another solution past 50, but we are only interested in between 0 and 50. So we're going to say x equals 3.4. Now, and again, my question needs editing. My apologies. Find the values of x for which the volume of the box is 30,000 centimeters, correct to 2 decimal places. Okay, so we're going to get 3.46 or 35.46 centimeters. So if x is 3.46 centimeters, if we only cut 3.46 centimeter squares out of the corner, we'll get a volume of 30,000 centimeters. Or if x is much bigger, 35.46, so we cut huge squares out of the corners, we'll then end up with a long, tall, thin box, and we can still create a box with 30,000 cubic centimeters. Okay, so we have two values there. Apologies for the errors in that particular question. All right, the last example and the last kind of question is the category 3 examples where we're essentially finding an equation given some points. So a stone is projected vertically upwards, projected upwards from the edge of a platform, and its height above the ground is measured periodically. The following results were obtained. So after 1 second, the stone is at a height of 10 on 3 meters. After 3 seconds, the stone is at a height of 4 meters. And after 5 seconds, the stone is at a height, sorry, I think I said height is at a stone before. Stone is at a height of 2 meters. So if the relationship between h and t is quadratic, find h in terms of t. Okay, so bringing this back to what the question really is mathematically. The question is, find a quadratic equation that goes through the points 1, 10 on 3, 3, 4, and 5, 2. So we've done this before, finding equation of a quadratic given 3 points. So we want to start with the most general form, okay? Now I'm going to use function notation so I can make my substitutions easily. So h of t is a quadratic, so at squared plus bt plus c. And we're going to make 3 substitutions. So h of 1 when t equals 1, h is 10 on 3. H of 3 when t equals 3, the height, or the value of the function, the height is 4, and h of 5 is equal to 2. Okay, so we have 3 points, subbing in 3 points, generating 3 equations in A, B, and C that we can solve simultaneously. Okay, so menu 371. No, sorry, before I do that, I've got to define my function. I'm just going to do menu 15 and delete that last question. Okay, so menu 11 to define h of t, and it is a times t squared plus, remember you need the multiplications, b times t plus c. Okay, good. Now we want to solve our simultaneous equations. Menu 371. We've got 3 equations and the unknowns are not x, y, and z. They are a, b, and c. Okay, and we are going to write our equation. So h of 1 is equal to 10 on 3. H of 3 is equal to 4. And h of 5 is equal to 2. Okay, so we get a equals negative 1/3, b equals 5/3, and c equals 2. So therefore, the equation h of t is negative 1/3 t squared plus 5/3 t plus 2. Now, sketch the graph of h versus x for suitable values, h versus t for suitable values of t. What is the height? Okay, so we now want to use this equation. So in my CAS, I want to take my defined function, which was h of t up here, scrolling up, I'm going to press enter, and now I want to substitute those values of a, b, and c into that. So given that, a, b, c is that. Okay, so now if I were to type h of t, I would get this. Okay. Now, over in my graphing screen, so over here, delete, delete, delete 3 times. We've got a really strange window here, so menu 4/5 to set it back to normal. Tab. Now, if I type h of t in here, I think it's going to give me 2 problems. H of t, right, the first thing it's asking me about is sliders for A, B, C, and t. Now, it's a bit frustrating about the A, B, and C because I have actually already substituted numbers in place of A, B, and C, but it's still remembering the A, B, and C. So I don't want to do anything about sliders here. I also don't want a slider for t because t is actually meant to be the x-axis, and that's one of the problems. I want to press cancel here. Okay, tab. I don't want to draw h of t. I need it to have x's in it. My CAS can only draw functions with x in them. So I want to replace all the t's with x, and that's quickly and easily done by drawing h of x. Now it's still going to ask me about the sliders for A, B, and C. I don't want sliders at all. I can just press cancel here. It knows what A, B, and C are. I don't know why it asks me. Right, there's my parabola. Sketch the graph of h versus t for suitable values of t. Okay, so we know it's a parabola. We can see what's happening there. We can see from the equation the y-intercept is at 2. Again, I wouldn't do any calculating here. It's a parabola. I'd go back over to my calculator. I want to know my y-intercept. I can do h of 0. If I want to know my x-intercepts, I can solve h of t equals 0 for t. Okay, negative 1 and 6. And if I want my turning point, I can complete the square. So menu 3, 5, h of t, comma t. Okay, so I know that this equation, I'm just going to write that turning point form out here. So h of t, actually I'll put it up here. This is also equal to, now the notation's a bit awkward, but it's still going to have a negative 1/3 there. It is t minus 5 on 2 squared, and then it is plus 49 on 12. So sketch the graph of h versus t. We've got our turning point from there. I've calculated my y-intercept and my x-intercepts here. 49 on 12 is just a bit more than 4, just in terms of scale. So we can think about what's happening here. The other thing I would say to you is, whilst you don't want to draw the graph back to -1, I think in terms of getting your shape right, it's helpful to think about. You have 1, 2, 3, 4, 5, 6. So my x-intercepts are going to be at 6, 0, and we're not going to draw past then. Suitable values of t. T is time, can't have negative time. H is height, can't have negative height. So we're not going to go past this x-intercept, which is at, 6, 0. We've got another x-intercept back here, but I'm not going to draw that one, okay? But I am sort of thinking about, okay, let's mark in the turning point, 2.5, and, we need a y scale first. 1, 2, 3, 4. Okay, so my y-intercept is at 0, 2. My turning point is at 2.5 and just a bit more than 4, so somewhere up there, okay? All right, so sometimes it can help you to think about like sort of starting from down here when you're drawing your shape, okay, to get the shape right. But you wouldn't draw it in past the y-axis. All right, so we've got, our turning point at 5 on 2, 49 on 12. We've got our x-intercepts marked. We've drawn for suitable values of t only when time is positive and only when height is positive. Okay, we should be able to answer all our questions now from the graph. What is the height of the platform? So the stone was initially projected from a platform. We can see from the graph that the initial height was 2 meters, so the platform was clearly 2 meters. From the moment the stone is projected, how long does it take to reach the ground? So we can see that the height is 0 when t equals 6. So it takes 6 seconds for the stone to reach the ground. What is the maximum height reached by the stone? 49 on 12 meters. If you want that as a decimal, Control Enter over here. See, it's a recurring decimal, so always answer exactly unless told otherwise. I'm going to leave that as 49 on 12 meters. You could write it as 4 and 1/12 if you want, but I'm not a big fan of mixed numbers. Okay, and that's the end of our applications of polynomials videos.